Chapter 18, Practical Electricity. First, you should be able to describe the use of the heating effect in appliances such as electric kettles, ovens, and heaters. So such appliances have a heating element, which is usually made of long, thin wires of nickel or iron, chromium, aluminum alloys. So you remember the formula, R equals to rho L over A. If you have long wires, which means your length is long, you have thin wires, so a small area. The result is that you have high resistance. Okay, so such heating element is able to withstand high temperatures as well as produce high temperatures. So these heating elements usually have very high electrical resistivity. So the formula is rho. Okay, the symbol for heating element looks like this. One line with 4 squares side by side. Next, please read up on the heating effect of electricity in the appliances, such as the electric kettle, okay, the convectional oven. As you can remember the name, convection means there is convection current involved. Next, electrical heater and the filament light bulb. For the filament light bulb, it actually uses a tungsten coil, okay, to produce heat as well as light energy. So once again, they use a tin. You can revert back to the formula, R equals to rho L over A. If if area is low, your resistance is high. Okay, next, this is where the formulas or calculations for this chapter comes into play to check the electricity consumption. So first, let me introduce to you a new formula. P equals to VI. Power equals to voltage times current. Okay, so using this formula, P equals to VI, and our previous formula from Ohm's law, which is R equals to V over I. Using these two formulas, equation 1, equation 2, we can derive the other forms of P. So you get this, P equals to V squared over R. You can derive it as P equals to VI. You sub in I, which is V over R. You get V squared over R from Ohm's law. Derive this, P equals to VI. Sorry, P equals to VI. You sub in V equals to IR. You get formula P equals to I squared R. In exam, you don't have to memorize the two different forms. You just need to memorize this. P equals to VI and Ohm's law. R equals to V over I. Okay, so in the previous chapter, we also learned that power equals to work done over time. It's how much work done or how much energy you output per unit time. So similarly, work done is just energy over time. So you get this equation, P equals to E over T. Okay, the third equation that we'll need for this chapter. So combining both P equals to VI, equation 1 and equation 3, we'll get this equation. Okay, let me rewrite it for you. VI equals to E over T. Using equation 1 and 3, you get E equals to VIT. Okay, here. So usually for energy consumption, we will have the energy in kilowatts per hour. So your P, as you know, the units is in watts. We try to convert in kilowatts. The time usually is in seconds. We convert it to hour. So together, the units for E will be kilowatt hour. Here. Okay, so using that kilowatt hour, we can actually find the cost of electricity. Okay, so the cost of electricity goes by cost equals to the energy, VIT, and this will be given to you, unit cost. And you multiply them together, you'll get the cost that you will need to pay. Okay, pause here to try the work example, as well as this work example. Okay, next. Dangers of electricity. There's 3 different hazards that you need to know of. Damaged insulation, which looks like this. Okay, it will cause electric shock if touched. Overheating of cable, when you overload the socket, okay, causes overload, or using inappropriate wires. Okay, you draw out too much current, okay, and then it causes a fire. Damp conditions, okay, it lowers the resistance of the body drastically, which can lead to electric shock. Okay, some safety features in the Home 6.3. So first, there is a circuit breaker. Okay, so for circuit breaker, they are always connected to the live wire. Okay, so if there's a high current, just cut off, and they can be easily flipped and reset. Okay, next one is the fuse. So fuse is also connected to the live wire, but they cannot be reset or just flip with a switch. Okay, they have to be replaced after it blows each time. So how a fuse works is that you can see that there's this very thin wire in the center. So that's why the symbol is like this, with a thin wire in the center. So what does this thin wire do is that when a high enough current passes through it, which exceeds the fuse rating, the wire heats up and melts. So if it melts, it becomes a open circuit, something like this. Okay, so it disconnects the cables or the appliances from the high potential or the source output. So for fuse, they come in, usually they manufacture in a certain specific rating. Okay, so for fuse users, or how do you install a fuse, you usually have a fuse that is slightly higher than the necessary current. So for example, if the appliance of a lamp requires only 4 amperes of current, you usually put a slightly higher one to match, because between 1, 2, 5, 10, and 13 ampere, 5 ampere would be the most suitable fuse. Okay, unless the appliance is of high technology, and then they will manufacture a fuse to be as close as possible to the current, the operating current. Okay, next you have switches to break the circuit whenever the appliance is not being used. Remember, they are also placed on the live wire. So when you open the switch, the live wire and appliances are disconnected from the high potential. So the electrical symbol, how to draw a switch, is just like a circle. Okay, you also can draw it this way, complete black dot. This is an open switch. This is a closed switch. Okay, next, we have a 3-pin plug. Okay, most of our house appliances use a 3-pin plug. You need to memorize that. The brown wire is the live wire. The blue wire is the neutral wire. The earth wire is the yellow and green stripes. Okay, so current usually flows from the live wire to neutral wire. Okay, the safety features is the earthing. So only if the appliances have a damaged component or what, then there's excess current, then it will flow into the earth wire, or when there's an electrical fault. Okay, so as you remember, next one is earthing. So same thing, it works like an earth wire. So the symbol for earthing, we see in the previous chapter already, looks like this. Okay, and the earth wire is usually connected to the metal casing of the appliance. So if there's a big current, it flows from the live wire to the casing, and then it will flow down into the earth instead of to the user. Okay, to prevent electric shock. As you know, some appliances does not have the 3-pin plug, so usually it has a 2-pin plug. Then these appliances usually will have something called the double insulation. Okay, the symbol looks like this on your packaging, double insulation. Okay, you can pause it and take a look at the answers for the work examples. Okay, and finally, you can just look at the main electrical wiring for a typical house. Okay, where it starts with the power coming from the power station. Okay, it goes through the live wire, and there is a main circuit breaker. Then here is your electrical meter, where they will actually measure the amount of electricity you use, so they can charge you, and this way you get the cost of electricity. Okay, then it's connected to different appliances that you use in your house. Okay, and once again, take note that there's a earthing connected to the circuitry. Okay, that's all for today.